Hi guys, thanks for coming to my talk. I'm Soumik. Today I'm going to talk about quantum pseudo entanglement. This is joint work with Bouland, Fefferman, Vazirani, and Zhou, our friends and collaborators from Stanford, Chicago, and Berkeley. Let's start. Entanglement is a driving force of quantum computing. This has fascinated scientists, both old and new. This was the topic that won the Nobel Prize in Physics in 2022. But there is still a lot that we do not know about it. In this talk, I will give you a new property of this. Let's start with a motivating question. Why is this a motivation? This will become clear in the later slides. How much entanglement does it take to spoof the Haar measure? Concretely, what do I mean by this? Let's say there's no polynomial time distinguisher that can distinguish between many copies of a Haar random state and many copies of a state that I draw from a particular collection. Here's the question that we ask. How entangled do states of this collection need to be? Here's our result. We can get away with very little entanglement. Our result helps us in understanding random quantum states better. What are these states? These are states that we draw from the Haar measure. Now, these states potentially have many applications. But here's the catch. We need to prepare them in polynomial time. Can we do that? No, we don't know how to do that. And so, practically, these states have limited applications because they don't have polynomial-sized circuit descriptions. What's the solution? Scientists talk about pseudorandom quantum states. These are states that mimic or spoof Haar random states. In a way, they give you the best of both worlds. Why? Let's see. There are two notions of pseudorandomness. One is the statistical notion. They have a fancy name. We call them quantum T-designs. What are these? These are ensembles of quantum states such that when you have T copies of a state drawn from this, these are indistinguishable from T copies of a Haar random state to any distinguisher, no matter the runtime. In other words, these are statistically close. Now, unlike Haar random states, T-designs have many practical applications. For example, in randomized benchmarking, in quantum speed-up demonstrations in cryptography. Why? Because we can prepare T-designs in polynomial time. For example, we know that geometrically local random quantum circuits, these near-term devices, after a certain depth, they become T-designs. There's one more notion of pseudorandomness, the computational notion. In general, these require complexity theoretic conjectures, but these are standard conjectures. We have the notion of computationally pseudorandom quantum states too. These were first studied by Ji, Liu, and Song. Let's recap the definition. A collection is computationally pseudorandom if two properties are satisfied. The first property, if we give a key k, then there's a polynomial time quantum procedure to prepare a state corresponding to the key k. Second property, in general, this key is a secret. And if it is a secret, then there's no polynomial time distinguisher that can distinguish between many copies of a hard random state and many copies of this state. That is, mathematically, for all efficient distinguishers A, the following statement holds. I will let you stare at it for a few seconds and just say that negligible n here means a quantity that is strictly less than 1 over polynomial. This mathematical statement here is just a restating whatever I qualitatively said for the second point. Okay. Now we have introduced two concepts. What is the relation between these two? Entanglement and pseudorandomness. In general, we measure this in terms of the von Neumann measure across a partition of qubits, which is like across an equipartition of qubits. So I will go through state collections one by one and then see what the von Neumann measure is for each of these collections. Let's start with hard random. The von Neumann measure is near maximal, so close to n. This is also called Page's theorem. How about T designs? Also near maximal, as studied by these papers. Now let's go to the last collection, computationally pseudorandom quantum states. How about this? Well, here we have a lower bound by a simple swap test based bound, which was studied by G. Liu and Song again. We know that the von Neumann measure is strictly more than logarithmic. Is this bound tight? We prove that it is indeed tight. Here's our result in a new light. We saturate this lower bound that we just saw, and we give the first direct construction that saturates this lower bound. We give a low entropy pseudorandom quantum state. Also, by modifying our techniques a little bit, we give a way to tune the von Neumann measure for our state collection. So for a wide range of measures, we get a wide range of pseudorandom state families, starting from that lower bound to the near maximal region. Let's come back to our motivating question. The answer is yes. We can spoof the Haar measure with exponentially less entanglement. Now I will briefly tell you about our construction. The idea is to start with phase states of this form. Now, G. Liu and Song and Brakarsky-Shmueli later, they observed that if we pick the phases of this state by any quantum secure pseudorandom function of this domain and range, then these are valid pseudorandom quantum states. What's a quantum secure pseudorandom function? So let's say I'm given a black box, which is promised to be a random function or this function. Then no polynomial time distinguisher can tell apart these two cases by polynomially many queries to this black box. Okay, back to our state. We start with this phase state. Then we just relabel the registers to rewrite the state in this form. This is nothing fancy. This is the same state, just relabeling things to make things a little convenient. So we have two registers, and you see this relabeling. Now, just for analysis and just for convenience, let's do some more relabelings and restructurings. Let's consider this object, which we define to be a pseudorandom matrix. Once again, nothing fancy. It's a matrix which is just a collection of the phases of this phase state. Why is this something that we did? Well, the cool thing is, once you define the pseudorandom matrix as this, then you can rewrite the reduced density matrix on subsystem A or B in terms of the pseudorandom matrix. Now, why did we need to do this? Well, if you do this, then the von Neumann measure can be upper bounded by the logarithm of the rank of this matrix. It follows by a simple Jensen's. The rest of the proof is now concerned with two things. One is reducing the rank of this matrix. That will automatically reduce the measure. And the second is doing it in a way such that no adversary can detect it. How do we naively reduce the rank of a matrix? Just repeat the rows. So for example, let's say we have a new matrix CF prime that we construct from CF. How do we do that? Let's say we take the first 3 rows of CF prime, the first 3 rows of CF, delete the second and third rows, and just copy paste the first row and the second and third positions. And do this for many other rows. Note that CF and CF prime have the same dimension. CF prime just has a lot of row repetitions. However, this is not sufficient. Remember, we had the second condition. The second condition was to make sure the rows that we repeat, they are not detectable by a distinguisher. So how do we do this? Well, first of all, let's repeat the rows in a systematic way. Let's say we consider a 2 to the k to 1 function g, so that the ith row of CF is the gith row of CF prime. Because G has a lot of collisions, automatically CF prime will always have a lot of row repetitions. And now, to ensure security, we will construct G in a very special way. We will let G be a composition of 2 quantum secure pseudorandom permutations with respect to a certain modulus. Why did we do this again? Well, now, by just a sequence of hybrids, we can show this fact. We can show that if CF prime is distinguishable from a random matrix, then G is distinguishable from a random function. Now, for a particular value of k, let's say k equal to log square n, G is actually not distinguishable from a random function. And we can prove this by the collision bound or close cousins of the collision bound. Now let's do the contrapositive. So G is not distinguishable from a random function. That means CF prime is not distinguishable from a random matrix. That is, it is a valid pseudorandom matrix. Then, by techniques of these papers that we saw before, we can say that the corresponding phase state is a valid pseudorandom quantum state. So we get our pseudorandom quantum state, and the feature that this has is that the von Neumann measure is bounded by log square n. So we get what we wanted. But this is not all. I promised you that just by modifying our process slightly, we can tune the von Neumann measure too. Let's see how to do this briefly. The target, say, is to construct a pseudorandom state collection where the von Neumann measure is k. How to do that? We start with a collection where the measure is n, that is near maximal. Note that this is not trivial to do. Why? The upper bound of n, that is trivial. But the lower bound is technical. The lower bound is something that we prove by considering phase states of a very particular special form. And that is the technical novelty. Then once we start with this, we can, by similar techniques to before, reduce the von Neumann measure to k by row repetitions and proving security. Let's consider this concept again. Quantum pseudo-entanglement. So two states, two collections are said to be this. If, when given a key k, we can prepare states corresponding to this key in both the collections. Also, Fn and Gn in general will be two different functions. So these two collections will be hiding some von Neumann measure. And this is the concept that we just discussed. What does our result say? Our results say that these collections of states, they exist in the strongest possible sense. The gap between Fn and Gn is maximal. It's n and polylog n. Before that, and a second feature of our state is that these states that we construct, these are also valid pseudorandom quantum states. Previously, the gap that we knew, that was a constant. And that followed from the paper by Georgiou and Hoban. We improve this gap and we make it near maximal. Applications. Entanglement is very closely related to the spectrum of a quantum state. So if we can do certain tasks that have to do with filling the spectrum of a quantum state, then these can be bootstrapped to construct distinguishers of those secure state collections that we just constructed. For example, let's say computing the Schmidt rank of a special class of states, or for example, computing the largest component of the spectrum of a special class of states. So our results show that we cannot do these tasks in polynomial time. It's the same for distillation protocols. If we can do this too well, then again this implies a distinguisher that breaks the security of our construction. Our constructions are also relevant to quantum gravity, this duality, but I will not go into the details of that here. Future directions. Two very important directions that I want to share. One is preparing these states by near-term devices, things that are geometrically local and have restricted depth. Can we do that? And secondly, applications of our concept in quantum cryptography or quantum complexity theory or different places in computer science. If you guys can think of anything, do let me know. Thank you.
Yeah, please wait the 5 minutes question to leave. Any questions?
Yeah, nice talk. It seems like the JLS result that you need super logarithmic entropy is sort of tied to the multi-copy PRS setting. But if you look at single copy PRS, you don't even need entanglement. So is there a result that sort of relates the amount of entanglement required and the number of copies of PRS?
So I didn't get the question fully. So what did you mean by multi-copy and single copy?
So you are considering the JLS result that you need super logarithmic entropy
Yes.
would probably work only in the multi-copy setting.
Yeah, it works when you have like more than 2 copies.
Yeah,
because
so
of the
one
swap
copy, you don't even need entanglement, right?
So like you mean that like the statement is that like a state collection, there's just one copy of the state that you're given, and that one copy is not distinguishable from a hard random state.
Yeah.
Yeah, right, okay.
So
that
the JLS
swap test
result,
lower bound doesn't hold there, yeah.
so JLS result works for
It holds for more than 2 copies.
okay, even
yeah.
2 copies it works, okay.
Yeah.
More questions?
Hi, thanks for the talk. So, pretty technical question. So, when you construct G, you use 2 random permutation. Why do you need 2 instead of just 1?
Sorry?
So, when you construct the G function,
Yeah.
you use like F1 and F2. So, you need 2 permutation. Why do you need 2 instead of just 1?
Oh, why do we need to? Like, that's because of the proof technique. Like, so the proof technique works by like so like the way we prove this is we have like a parent pseudorandom state that has like maximal von Neumann measure, and then we somehow tune that to like reduce the entropy. So it's like a part of the proof technique. Like we can discuss that like detail later.
So let's talk about linear, right? Okay. Any questions?
Thanks for the nice talk. When you construct families of pseudorandom quantum states with entanglement that scales as n, how do those constructions look like now?
Yes, right. So the way we do that is we compose 2 functions, a 4-wise independent function, like with quantum secure pseudorandom permutation. And why do we need this 4-wise property? So when we are proving the lower bound, we basically try to bound the von Neumann measure, like lower bound it, by the negative logarithm of the Frobenius norm. And so there's a square in the Frobenius norm. That's why you have 4 terms. And so to make it simple, like when we're applying like some sort of a second moment bound, let's say, to bound it, we consider this 4-wise property, and then the quantum secure pseudorandom permutation is due to like security of the construction.
Have you or others considered like an analogous notion of like pseudo-entangled pseudo
Unitaries, right?
Like
yeah,
for
that's
unitaries
a
where
great
they're like
question.
indistinguishable from hard random?
Yeah, that's a great question. Like that's a great question for future research. Like we are thinking about it, but we don't have a lot right now. Yeah.
I know you didn't get a chance to go into like the ADS-CFT like connections in the talk, but are there any particular resources that you'd point interested students to learn more about that direction of things?
ADS-CFT. So there's a paper by Bouland, Fefferman, and Vazirani which talks about like the connection between like ADS-CFT and let's say complexity theory, and how like let's say like certain objects in ADS, like geometry of certain things, they map to properties of quantum states in CFT, and how if we know more about quantum states in CFT, it tells us about the geometries of those structures, and how that implies something about the dictionary that's like mapping between these 2 like different walls. And so maybe that paper, yeah.
So before we leave, just 2 announcements from the organization. So first, the dinner is at 7 at Alt Wiesmann. And coffee break is now at UFO. And I think with that, we can thank again Soumik.